Alright, hello everyone. In a few moments, you're going to be going over the reading with me, or rather, I will be reading it to you. Let's talk about some vocabulary and an important concept before we start the reading, just so that you guys will understand what that stuff is before we actually get into that reading, okay? So, orbit. An orbit, in this case, is the circular path of an electron traveling around the nucleus. This is similar to a planet's orbit around the sun. Light. I'm sure you know what light is, but could you give a definition for light? Well, light is a form of electromagnetic radiation that lies within the visible range. And speaking of electromagnetic radiation, there are many types of electromagnetic radiation. You know, electromagnetic radiation is waves, right? Like light waves, radio waves, X-rays. And you can have waves with long wavelengths, and you can have waves with short wavelengths, and you can have everything in between. And that progression, right? Like all of those possible types of waves, if you spread them out, like right here, you got long wavelengths and short wavelengths and everything in between, and if you put those on this kind of a scale here, we call that the electromagnetic spectrum. It's all of these things. At one end of the spectrum, with the short wavelengths, are the gamma rays. They also have the highest frequencies. At the other end of the spectrum are radio waves, which have the longest wavelengths and low frequencies. So light, visible light, just refers to just these right here. Just these waves. And if the waves get too long, then they're not visible anymore. And if the waves get too short, then they're not visible anymore. Human eyes evolved just to see these wavelengths. So when we talk about low frequency or high frequency, what are we talking about? Well, we're not talking about wavelength. That's something different. So what is frequency? Is it how high the wave is? No, it's not how high the wave is. That's amplitude. Frequency is like if you just look at one point, and if this wave is moving, and I just put my cursor right here, and I just see how many waves go by my cursor in 1 second, that's how we measure frequency. It's the number of waves per second or cycles per second. And we measure frequency in units called hertz. 1 hertz is equivalent to 1 wave per second. So if I put my cursor right here, and this wave is moving, and I'm counting, okay, every second, click, 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 every second 1 wave goes by. Well, that's 1 hertz. What if I'm measuring this wave, and let's say 5 waves are going by every second? So I'm measuring click, 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 and every click 5 waves go by my cursor. Well, I know that the frequency of that wave is 5 hertz. And if I've got 100 waves going by every second, then I know the frequency is 100 hertz. So wavelength, when we're measuring how long a wave is, how do we actually measure that? Well, we pick a point on one wave, and then we pick the exact same point on a different wave. And in this definition, they're saying that the distance is measured from crest to crest. But if we measured from trough to trough, wouldn't it be the exact same measurement? Well, yeah, it would. What if we measured from midpoint to midpoint? Would that be the exact same measurement? Yes, it would. But technically we're going from crest to crest. And however long that is, that's the number that we use for the wavelength. And finally, photon. A photon is a quantum or discrete packet of electromagnetic radiation that has a given amount of energy. And probably the best way to think of a photon is it's like a little particle of light. We call it a packet of light sometimes. And it's quantum, or it's discrete. We say that because you can't like break it in half. Okay? You either have a particle of light, or you don't have any light. Right? It's either there or it isn't. It's off or it's on. There's no little bit of one photon. So when you have these photons, you either if you have one photon, then you have one photon. If you have two photons, then you have two photons. But you can't have like 1.5 photons. That's what quantum and discrete means. It means you can't break it up into pieces. Take the whole thing or nothing. Alright, so another thing that I want to kind of tell you about, it's going to be in the reading, but I want to talk about it a little bit before you actually see it in the reading. Remember, after Rutherford's gold foil experiment, we knew that the positive charge was concentrated in a hard, dense nucleus at the very center. It was very small compared to the whole atom. And the electrons were not in the nucleus. They were somewhere around the outside. But we really didn't know anything more than that. We did, however, know that when you put gas in a tube, remember the hydrogen gas? When we put it in a tube and we ran electricity through it, we knew that we only got a couple different kinds of light, right? I think there was 4 kinds of light, and they came out at very specific frequencies. A very specific kind of red, a very specific kind of blue, a very specific kind of violet. And scientists started to kind of think about why this might be. And as you're going to see in our reading, one of Rutherford's students, actually, Niels Bohr, he started to think about what could explain these specific kinds of light that were coming out of atoms. And somehow, I don't think I would have been smart enough to come up with this, but he started to picture an atom where electrons could exist at different positions around the nucleus. And we now know that as electrons are being added to an atom, they like to be as close to the positively charged nucleus as possible. Negative electrons are attracted to positive protons, of course. And when another electron comes in, It's coming by. It feels the pull of the positive charge, and it wants to be as close to the nucleus as possible, but it can't be here because this ring is already full, basically. Okay, seats taken. So he can be close, but he can't be as close as these guys. He has to take a seat in the next row. That's as close as these other electrons will allow it to be. And as more electrons are added on, they'll fill up the rest of these rings. And then Niels Bohr began to think, well, maybe there is an energy associated with each level. And if you can get enough energy, if this electron can get enough energy, well, then maybe it can move up to a higher level. Uh-oh. Maybe it can move up to a higher level if it can get that extra energy. Remember, in negatives, this is a lower number than this because it's negative. And the more energy you add, well, then the higher it can go up. So energy is coming in. That energy causes the electron to go up. But here's the thing, that electron doesn't like to stay up there. That electron still wants to be as close to the nucleus as possible. So he's a little uncomfortable up here. He's a little unhappy. So what is he going to do? Well, he's going to get rid of that energy as quickly as he can. But when that energy comes out, it's different. It's different than when it came in. And that transition, as you saw from your electrons and light activity, okay, moving from outside to inside, produces light at a certain wavelength. And the reason that it's always a specific frequency of light is because the frequency is determined by, how much this electron changes, and it can only change from one ring or one shell to another shell. It can't go, halfway, and it can't go a third of the way, and it can't go anywhere in here. It has to go from one shell to another, and that produces light at a certain frequency. Okay, going from this shell to this shell is a change that produces light at a certain frequency. And if you have multiple electrons all absorbing energy, right, and they're all going up to different shells, and they're all making different transitions, well, that's how you can get more than one frequency of light. Sometimes you can have four frequencies of light, Sometimes you can have 8 frequencies of light from one element. Sometimes you could probably have 160 specific frequencies of light. But that's still not very much when you consider the infinite amount of frequencies that you have on the electromagnetic spectrum.